Welcome to the demonstration on troubleshooting IP multicast, particularly protocol-independent multicast sparse mode or PIM-SM on Ruckus ICX switches. I'll be showing you how to use the tools provided by the ICX operating system for collecting data to resolve an issue, or possibly multiple issues, that are preventing a multicast stream from reaching an IGMP host. First, let's take a look at the environment I'll be working in. I have a terminal application that allows me to telnet to each of the switches in my lab. Each tab on the top represents individual connections to each of the 4 routers in my network. These 4 routers have been pre-configured for full IP routing, and there are some issues to be discovered related to multicast. Here's the topology we'll be working with. We have a server on the left generating multicast traffic using destination multicast address of 239.0.1.2. It's connected to a router with PIM sparse mode enabled. That router has 3 neighbor routers. Below it is the Rendezvous point router for this PIM domain. To the right of it is the Bootstrap router for the PIM domain. And down and to the right is another PIM-enabled router with a client attached. This client should be sending IGMP membership reports to the router, informing it that it wants to receive the 239.0.1.2 multicast stream. This is the client PC. On it, I have a small application that listens for multicast traffic for the group address of 239.0.1.2. Right now, it's not receiving any traffic for this multicast group address. Before we jump into troubleshooting a multicast problem, we should always verify we don't have a problem at a lower layer. I've already used LLDP to verify the entire physical topology, so the image I showed you earlier has been verified. Now we should verify the basic IP connectivity between the server and the client. We can do all of this from the ICX CLI. So from the server router, I'm going to go ahead and ping the client from the server router's interface that is on the same side as the server itself. So the server address that's sending the multicast traffic is 144.49.10.100. And the client that's requesting is 10.10.200.100. So from the server-side router, I'm going to send a ping to that client IP address from the IP address on the router that's on the same subnet as the server, which verifies connectivity from end to end in this direction. So let's go ahead and do that. So we have a successful ping to the client PC, the one that's requesting the multicast group address, sending membership reports, trying to join multicast group 239.0.1.2. So I have a successful ping from my router interface on the server subnet that reaches me there. So I have good IP connectivity that way. So we'll run the same test from the client-side router. We'll get over there, and then we'll run the same test and ping the multicast server and just make sure that we should have full end-to-end connectivity. This is useful for us, and why I do this all from the ICX CLI is there might be occasions where you have server administrators who manage servers, and they won't allow you to get on their servers and run pings directly from the server or the client. So you have to do the best you can with the tools you have, and the source ping on the ICX is a great way to do that because it essentially simulates that client originating the ping to a destination host. So let's go ahead and run that ping again here. And again, this is pinging the actual server from the IP interface of the router that connects to the client subnet. So again, successful ping. So everything's looking good from an IP connectivity standpoint. So we have full basic unicast IP connectivity. We're just having a problem with multicast getting through here. So what we've just done is verified basic IP unicast connectivity from the client subnet to the server and from the server subnet to the client. So we've just verified that we have full connectivity between them in this topology that we've talked about. So the next thing we need to do is we need to verify that the client router is seeing these IGMP membership reports from the client, because if the client's not actually sending the reports into the router, there's no way for it to associate that client as a receiver for a multicast stream that it might know about. So let's go ahead and do that first. So over here at the client router, we're going to run the show IP IGMP traffic command to see if we've received any IGMP membership reports from the client. So let's take a look. So we are seeing member reports, version 2 reports on port 119. This is the port that the client's on. We have 18 membership reports that have come up. So this looks good so far. It looks to, from my perspective, that we are seeing membership reports coming in from the client, so that's good. So let's take a look at the show IPPIM group command. This command tells us what groups that are being registered or being requested by that client. So let's take a look at that one right now. So this output shows us that a membership report has come in for port 119 right here on VLAN 40 for the group address of 239.0.1.2. So we are seeing the client requesting to join that group and receive multicast traffic destined for group address 239.0.1.2. So the client side looks good. And keep in mind, when we're looking at multicast, we want to try and troubleshoot this from the outside in. So before we start digging into what's going on inside the network, we want to know that the edge devices at the end, the server and the client, are doing their part. So next thing we're going to do is we're going to take a look at the server side. So on the server side, what we're looking to find out is from that server router, do we see this multicast traffic stream coming in from the multicast router itself? Because of course, if the router is not sending the multicast traffic to the router, there's no way it's going to forward it to the client on the other end. So that's what we're going to take a look at next. So looking now at the server router, this is the source router over here that the server is connected to. We have some commands we can run to see if we have the source group entry for traffic coming from that server. Now, we wouldn't build a source group entry if we didn't know that there was a multicast source sending multicast traffic to us as a PIM router. So we'll go ahead and run that command right here and check that out. So we use the show IPPIM mcache command, and this will show us what multicast traffic we've seen on the router. So we have one mcache entry right here. It is sourced from 144.49.10.100. That's the host, the server that we know is sourcing the multicast traffic. We ran the ping to it earlier to verify we had connectivity and everything looked good. And what it's sending is sending to multicast group address 239.0.1.2. So this is the correct multicast group address. It's the same one the client's requesting. We have a server sending this multicast traffic. So, now we can start looking into the rest of the network to try to figure out what's preventing that traffic from getting from this source that's sending multicast traffic that we know is being sent to a host that we know is requesting that traffic to be received at it. So, let's take a look at a couple things. So if we go to the client side and the server side, this is something we want to check from both. We want to know if they both know that a bootstrap router even exists on this network, because for PIM to function, it uses the concept of the bootstrap router that knows about the rendezvous points for the different multicast streams, and rendezvous points are the ones that facilitate connectivity for a multicast stream. So the first thing we want to do is check the top level of that hierarchy and say, hey, is there a BSR here? So we're going to run at the source server router and at the client router. We're going to run the show IPPIM BSR command and see what output we get. So over here at the server side, we know of a BSR. It's at 8.8.8.8. I have a BSR router out there. That's the loopback address of it. So I know this is correct. So great. This router knows about the bootstrap router. So now let's go over to the client side and check its knowledge of the bootstrap router. So here we have the same information. It is aware of the bootstrap router and knows it's out there at 8.8.8.8. So everything looks good from both ends, that they know who the bootstrap router is. So now let's go over to that bootstrap router and find out what it knows about rendezvous points, because again, this is the router that informs of the RP addresses to find those rendezvous points to facilitate the connection of multicast streams between servers and clients. So we'll come over here and we'll take a look at what rendezvous points it knows of using the show IPPIM RP-set command. So what we have here is we see a group prefix learned from the BSR. It knows of a rendezvous point at 3.3.3.3. That is my rendezvous point router that's configured for this RP functionality. And the group prefix is 224.0.0.0 with an 8-bit prefix. So I think that might lead us all to a little something right now. But let's dig a little further and see what else we have. So let's go over to our server router one more time. And I know we're hopping around a little bit, but that's kind of what you're going to end up doing when you're trying to troubleshoot a multicast problem, because there's so many players that you need to kind of look at each one's perspective to understand what's going on. So over here, we're going to look at the rendezvous point hash that it has for our group address that we're looking for. We're looking specifically for the 239.0.1.2. So we're going to run the show IPPIM rp-hash command with that group address to see if we have an RP with an entry that supports that group address. So show IPPIM rp-hash 239.0.1.2. So basically what this is saying is I know of an RP, but I don't have any that have this group address available to me. So that's a bit of a problem for us. So now let's go look to why our rendezvous point isn't connecting us or providing a connection point for this prefix. So here's our RP router. We haven't looked at this guy yet. So what we're going to look over here is we're going to do the show IPPIM RP candidate address, and we're going to see what multicast prefixes that this particular router is capable of being a candidate RP for. Now in PIM speak, all RPs are candidate RPs. They can be the rendezvous point for a multicast stream, but they have to be set up to do so. So we'll check out what this one's ready to do. We'll do that with the show IPPIM rp-candidate command. So this is a rendezvous point. It's 3.3.3.3. That's the loopback address on this router. So that does match with what we saw earlier when we looked at the BSR about known rendezvous points. And the group prefixes it supports is 124.0.0.0 with an 8-bit prefix. So basically what that's telling us is this thing only supports multicast group addresses right now that start with the 224 first octet of the IP of the group source address. So this is going to be a problem for us. Ours is 239, so this doesn't match. This prefix filter that is set up here for who this RP is going to be a candidate RP for doesn't match our prefix. So what we're going to do here is, and this is something different schools of thought, but in mine, you want to know which multicast group addresses you want to support on your network, and make your RPs specific for those group addresses as opposed to opening it wide open to all of the Class D multicast group addresses that are available. So what we're going to do here is we are going to get into this router and we are going to set it up as a candidate RP for the 239.0.1.2 multicast group address. So we do that with, we'll get into config T, and we're going to get into router PIM. And in router PIM, we are going to make this we're going to configure the RP candidate to add a new prefix for the 239.0.1.2 multicast group address, and then we have to apply the mask. And we're going to apply a full 32-bit mask, meaning specifically this one multicast group address and not, say, everything in the 239.0.0.0 range with, say, an 8-bit mask. So let's do that. This is done with the rp-candidate add command. And the mask here is 32. So we're rp-candidate add 239.0.1.2 with a 32-bit mask. So now we've gone ahead and added that to our router, our rendezvous point router. And so now we should be able to go back to the server router and look to see, we'll run that show IP PIM RP hash command again and see if there's a rendezvous point now for the 239.0.1.2 network. So let's take a look at that. And sometimes this takes a while to propagate out. So we'll give it a moment here, and then we'll take a look again. Everything in this is not necessarily immediate because the RP has to go and register with the bootstrap router. The server router has to go out and communicate with the bootstrap router again to find out if there's an RP hash for this. And here we go. So now when we do the show IPPM RP hash for this multicast group address, we do get from the bootstrap router a rendezvous point of 3.3.3.3. It supports version 2, and we got that from our bootstrap router at 8.8.8.8. So everything is looking a lot better from the source router. And let's kind of see what we get out of this. So let's go back to our PC and see what we get there. So back at our PC, we see that we're still not receiving any multicast traffic. So while we got some things worked out from the server router's perspective about this multicast group address and a rendezvous point for this group address, our client's still not receiving it. So now what we'll want to do is we'll want to go back and look at our client router and see what it knows about the RP hash for that 239.0.1.2. Because remember, this is all routers need to know about this information to be able to facilitate traffic forwarding. So all of the routers in this traffic flow have to know that there's an RP point for this particular multicast group address. So back at the client router, we're going to come over here, and we're going to look to see if it knows that RP for the 239.0.1.2. So we'll do the show IPPM RP hash command again. And we're doing that for the 239.0.1.2 group address. And we have no RP available for this group. So while the server router does have a rendezvous point available for this group address, this router does not. Okay, now this is where things get a little interesting, and you have to really know a little bit about multicast to be able to continue further here. So here's what we know. We know we have an RP that is registered for this group address. We know the bootstrap router knows of this registration. We know that both of these routers, the client router and the server router, know of the bootstrap router and its availability. So when you know multicast information, you know there are a couple of ways that this could happen and why one router may not have RP hash entry for a particular group address. And it's usually one though. It's usually one problem. It's a reverse path forwarding problem, or RFP. So let's talk a little bit about reverse path forwarding. So RFP, or the RFP check in multicast, is designed to avoid any looping of multicast traffic. Basically, it instructs a router to compare an incoming stream against its routing table. So if a PIM registered RP hash is received on an interface, the router checks the RP address against its route table. Right? So in this case, the route table is going to show a direct link to that client router, and that's probably going to be the best path, right? So if this is the path that this client router would take to reach that rendezvous point and multicast stream, that's the link it expects to receive the multicast stream info from. But if it gets that from any other interface, it's going to reject it, and it's going to reject that RP hash entry because it thinks that there's a loop in the network that's resulting in this traffic finding its way to this router over a path that's not the shortest path in the network. This is probably what's happening here, and when you see a scenario like we're seeing, that's typically the direction you're going to want to look. So when you see this problem, what you're going to want to look for is most likely interfaces in that shortest path perhaps aren't configured for PIM. So let's go ahead and take a look at that. So back in our client router, we're going to check PIM's RPF for this bootstrap route, or I'm sorry, for this rendezvous point router, which we know is 3.3.3.3, right? Because that's where that's that rendezvous point for this traffic stream is the 3.3.3 router. So we're going to do the show IP PIM RPF command, and we're going to look specifically at the 3.3.3 IP address. And we have no RPF route to 3.3.3.3. So basically it's saying, I don't know how to get to 3.3.3.3 from an RPF perspective of verifying the reverse path. So let's take a look at our routing table and see if our routing table has a path to 3.3.3.3. And we do have an entry specifically to that address. It's out port 1123, but this still gives us useful information, right? So we have no RPF path, and that's probably because we're receiving that information about the router and the multicast stream through an interface that is not this shortest path. So the first thing we would do here is look at this interface right here, this 1123, and make sure that PIM's enabled on it. So we can do that a couple ways. One of the easiest ways is using the show IP PIM interface command. So we see here that we have interface 1124. We've got our VE40 and our loopback 1. So these all have PIM-SM enabled, but what we don't have is this port 1123. So the next step that we're going to want to do is we're going to want to go ahead and enable PIM on that interface. So this is done. So we'll get into config mode, and we'll get into the interface itself. So 1123, and we enable PIM on this with the IP PIM-sparse command. Oh, if I type sparse correctly, it'd be a lot better. Okay, so IP PIM-sparse is enabled now. So we'll take a look now and see if we see any neighbors on this interface, because PIM is a neighboring protocol where routers learn of each other over directly connected links. So let's take a look at this. So right now we have neighbors on port 24 and port 23. So now we have a PIM neighbor on 23. So that is our shortest path to that bootstrap router. This is based on our topology, and I'll show you that here again. Yep, so looking at this, we do see that the shortest path between the client router and the server router, and I happen to know this interface right here is port 23. So we neglected to enable PIM on that interface, and that caused the problems we're looking at right now. So now that we've enabled PIM, we should be able to go back to our client and see if we're receiving this multicast stream now. And yes, now we're seeing the stream appearing on this router. So we're getting traffic now on the 239, I don't think I can highlight this, but 239.0.1.2, we're receiving that, and we're incrementing counters for each of these packets that are being sent by our server over on the other end of the network that's been sending them all along, but this client hasn't been able to get them, and this is because we didn't have PIM enabled on the shortest path interface. So we had multiple problems here, and let's just kind of summarize those. The first problem we had was that we had a rendezvous point router that had a mask that didn't cover the range for this particular multicast group address. So we went into that rendezvous point router and we added this prefix or this actual whole group address with a 32-bit mask, so specifically this group address, and allowed it to be a rendezvous point for that particular multicast stream. So as soon as that happened, now when requests went out from any receivers, who wanted to join that group could find out about that rendezvous point router and do an RPF check and say, okay, the path I'm capable of receiving this multicast stream on, that I would be receiving this multicast stream on from this bootstrap router, should be the same path that I would use as a router if I were sending traffic to that rendezvous point router. In our case, that shortest path interface from the client router didn't have PIM enabled, so it was receiving traffic on a PIM-enabled interface that wasn't the shortest path to that rendezvous point router. So once we enabled PIM on interface 23, we were then able to start receiving this traffic because now the traffic's coming in from that rendezvous point on the shortest path that I would use and pass the RPF check requirement, and then allows me to start receiving this traffic and forwarding it down to the client. Well, that pretty much wraps up this demonstration. There are many other things in multicast that could cause problems for you. This was just a sampling of a few of the things, common things that this RPF check and not having PIM enabled, in our small network that we set up for this is really unlikely to happen, but still can. But I've seen this before in really large networks where you're spanning so many routers across so many different locations. You might see this. And you might see suboptimal paths being taken by multicast traffic, and your PIM routers rejecting that traffic because it doesn't pass the RPF check. It's happened a lot before. It's easy to miss, especially when you're talking about a network with hundreds and hundreds of routers. So in this small scenario, it's unlikely. But there are many other things that can come up in multicast, including problems with IGMP itself, the different versions of IGMP. There are some things particular to PIM dense mode that are a little bit different than sparse mode, but this is just a small little sampling of some of the things you can do and some of the commands that give you useful output of how to troubleshoot PIM problems. So hopefully this gave you a little something from this demonstration that will help you in troubleshooting multicast networks in the future. Thank you for viewing this demonstration and hope you come back for more in the future. Thank you.